So today we are having a lecture 14, EE341, EE341, microelectronics. Microelectronics. Right. So last time what we did, last two lectures, basically we are seeing the frequency response of an amplifier, and we are on chapter 11 of fundamentals of microelectronics book. So we will today also continue the frequency response. So we will talk about some examples following some conclusion or analysis point which we have derived in the last lecture, and some fundamentals which we have seen in the previous lecture. So I will just recall quickly what we have done in the last lecture. So we brought some analysis point that we can apply to find the frequency response of any amplifier. Okay. So those analysis points I just wrote in the last lecture too, but just as a refresher, I am writing them again. So those analysis points are basically, first thing and the most important thing we need to do is determine which capacitors, which cap impact low frequency response. Okay. So last time, if you remember, we separated the frequency response into overall three sections. We talk about low frequency response, we talk about mid-band, and we talk about high frequency. So low frequency, we mentioned WL, high frequency, we mentioned WH, and the mid-band gain was the area which we normally use to calculate previously when we want to see the gain of an amplifier. So we were all the time using the mid-band gain. So that DC gain, which we were finding, was ultimately the mid-band gain. So V out by V in. Right. But we also see in the last lecture something which is a omega L, a low frequency response. And what was that? That at some frequencies, which are relatively at lower point, the capacitance or the system has a high frequency response. High frequency response, system has a high pass filter response. What is high pass filter response? Meaning it doesn't allow frequency at low frequency, and it allows frequency at a higher frequency. And what we saw for this such configuration, when we have a capacitance, a series capacitance, Cin, or a DC blocking capacitor, or commonly known as a coupling capacitor at an input, this will ultimately lead to this omega L with the help of resistance, which is at this input side point. So based on this input, the capacitance is ultimately going to form a RC corner. And if you recall, that RC corner value was something biasing point, and we talk about Ri here. So we talk about this input or omega L was equal to 1 over Cin times Ri. That we have seen in the next lecture, in the last lecture. And then we also talked about omega H, which was high frequency response, and which was coming because of the something, it's a source follower, so something of the load capacitance and the impedance seen at this point. So omega H was basically R times R. It's not going to be R here, it's going to be 1 over GM times CL. So that's what we saw. So there is a low frequency cutoff and high frequency cutoff, and the low frequency cutoff comes out because of the input capacitance, or we commonly call as coupling capacitance, and the high frequency is because of the low capacitance. So we need to determine which cap impact low frequency response, and normally this one will impact the low frequency response, and another one we will see. The CL is not going to impact the low frequency response. And we also saw in the last lecture something about the parasitic capacitance. So whenever we do the low frequency response, we will ignore the parasitic, or we call transistor capacitance, CGS, CGD, CDB, and CSB for low frequency response. So we will not consider those capacitance which are inherited to the amplifier. ठीक है, तो हम लोग उनको ignore कर देंगे. Let me rub this so it's not confused. Yeah. After that, when we have decided this omega L, we concluded this thing, we'll find the old thing, the gain of the amplifier. We call calculate the mid-band gain. Calculate the mid-band gain. And when we can calculate the mid-band gain, what we do, we ignore both the capacitances. Either they are placed CL, Cin, or the transistor capacitance. So all the capacitances will be ignored in the mid-band gain calculation. Something similar which we were doing in the first almost 10 lectures when there was no frequency response. We used to find the gain V out of by V in of the system. And once we have done this thing, so we figured out WL point, we figure out mid-band gain, and now we are concerned about the high frequency response. And for the high frequency response, what we need to do, we have seen that we will do that from every node to ground. We will find capacitance. We will find capacitance. Okay, so we'll find capacitance. There will be CL load capacitances. And also there will be transistor capacitances. So now we will ignore the transistor. So transistor capacitance will also be involved here. And then node count, they are between node 1, which we call sense. So calculations, which are from node to the ground, which are from the node to the ground. So we'll separate these, and then we will apply the Bode technique, the Bode plot sort of stuff to evaluate the overall magnitude response of a amplifier. So it will tell us this complete analysis which we have seen. So let's apply these things to a couple of examples, and we will see how the things are move forward. And we'll apply basically to those same amplifiers which we have studied previously. So let's start with the basic one, which is the common source state. So I will write common source as CS. So we'll apply the same thing to the common source state. Okay? So we will see some interesting phenomena in the common source state. So, but before that notion, let me draw the circuit, and then we are going to bring that thing. But importantly, since at this moment we are analyzing, so we will analyze by starting with a low frequency response. So at this moment, I'm not talking anything about the high frequency response. I'm only concerned with the low frequency response. Okay? So we'll do in a high frequency too, but at the start, we'll do low frequency response. So let me draw the circuit. I guess let me use the black, that was more easier. I don't know, it's more linked with that thing. So we have an amplifier, so it's a common source. So we are applying an input on the gate, but now we are also having a coupling capacitor. Let's give it name C in. We have some input V in here and it's grounded here. Then we are having, since we are going to apply some biasing, so we are having some biasing point here, because this coupling capacitor is also used for the biasing. So we call it as a VDD. And also we have some resistance here. Based on the resistance ratio, we can set the values which we want to, R1 and R2. Let's give this node name as X. So this node is X. And what we call it as M1 for our easiness. And then we have here again a load resistance RD. And we're finding our V out at this point. And initially we're assuming this as a common source with degeneration. Okay, so we are having an RS here. So we are having common source with degeneration circuit with the Cin. We all know because of addition of this RS, what happens, or midband gain or ultimately the gain goes down. ठीक है, जब हम RS ऐड करते हैं, what ultimately happens, or gain basically goes down. So if without degeneration, the gain of a common source is minus GM. If I ignore lambda, it will be minus GM RD. But with the addition of gain, my go degeneration, RS, let me write. My gain will go down GMRD divided by 1 plus GMRS. So it goes down basically my gain. So, but it has in terms of noise, in terms of impedance, but how we can get benefit of these things if I just put again a capacitor which is a low frequency capacitor. This time मैंने कहा था ना, it's not only the Cin, we can have some more capacitance. Where are those capacitance? If I just plug it something here, CP, let's say. Another capacitance is a low frequency capacitance. Not only the Cin is a low frequency capacitance, this is also a low frequency capacitance. And let's observe its behavior, how this low frequency capacitance is operating. So if we want to move forward, let's write some background of this thing, that do the calculation, and we can do the frequency response afterwards. So first of, and the most important thing, we need to find V out by V in. Okay, so we want to find V out by V in, right? And I will bring now the capacitance of Cin in the equation. So this V out by V in is equal to, we all know, we can do the bifurcation, Vx by V in times V out by Vx. Okay, so we can do this thing. We can separate my Vx by V in as something equal to, so here R1 and R2 are in parallel, and then there is a Cin being applied here. So it's somehow voltage division. So if you want, I can simplify this thing as a blue. So I'm just simplifying this part. So here we have V in. Here we have impedance. Let me just write this as an impedance 1 over Cin. So I'm not writing anything, just replacing the resistance. And here we have, because in a small signal, it's going to be virtual ground of VDD. So it's going something like this. And this point is Vx. So that will make your life simple. Vx parallel R1 R2 plus CSN. ठीक है, so R1 in parallel with R2. So there's no, we don't have values. We don't want to open this thing, but this will be equal to Cin times S divided by 1 plus C sin R1 time parallel with R. So we can write this expression, and that is Vx over Vn. Okay? And that's basically just because of the biasing. So now what we can see, this is a what type of a response? A similar response which we have seen previously. This is ultimately a capacitance, and this one is a high pass filter characteristics. So ये फिर हमारे पास एक high pass filter characteristics आ जाएंगे, और वो high pass filter characteristics किस तरह के होंगे? That we can just see what will the values of this network, but that's ultimately forming a high pass filter characteristics, which are going to be something like this. तो हम लोगों ने बात की थी, so something like this. तो Cin का तो impact हम लोग पहले भी देख चुके हैं. It will be something similar impact as we are having. But now the important thing is that we also want to see, we'll just plug in the numbers here, but the important part for us is what's the response of V out by Vx. ये तो इसको high pass में cut कर देगा, but what CB is adding, because I also mentioned the CB in this case is a low frequency response, and वो क्या करेगा? It will be ultimately again bringing some high pass characteristics, and during the mid band calculation, what we do, we will ignore C in and we will ignore CB. Ignore का मतलब we will make them short. ठीक है, जब इनको हम शॉर्ट करेंगे, अल्टीमेटली व्हाट विल हैपन, द CB अगर इसको जीरो कर देंगे, शॉर्ट कर देंगे, RS will go down, RS will be zero, and RS will be zero और gain will be again minus GMRD. So हम लोगों का गेन इस तरह ज्यादा हो जाएगा, जो हमें एक नुकसान था कॉमन सोर्स डिजेनरेशन का इन टर्म्स ऑफ गेन रिडक्शन, वो हमारा खत्म हो जाएगा. And also by adding bypass capacitance, we are still getting the advantage of noise immunity and also the high input impedance. Whereas जो scene वाला काम था, again that will be considered shorted in the your DC gain calculation. But let's come back to the V out by Vx and see कि वो characteristics किस तरह के आते हैं. So let's do this V out by Vx. We all know this V out by Vx. Vx is ultimately अगर मैं gain find करना चाहूँ, Vx यहाँ है, V out वहाँ है, so it's going to be load. Again we are assuming R naught is equal to infinity, ठीक है, और lambda is equal to 0. So I can ignore small R naught. So now this RS is in parallel here, so we can write RS in parallel with over CBS plus 1 over GM1. ठीक है, ये वही चीज है कि अगर ये CB ना होता, if there was no CB, we will write the gain of this one will be equal to minus RD divided by RS plus 1 over GM, and that will be equivalent to जो हम लोगों ने यहाँ calculate किया था. But because of addition of CB, what we are doing, we are taking parallel of RS with 1 over CB. So now अगर इसका हम characteristics देखें, let's a little bit explore this one in the next, because we don't have space here, we can explore in the next one के ये relation क्या बनता है हमारे पास. So if we just do this math, the V out by Vx, ठीक है, will be equal to minus GM, and just opening up the same expression which was in the previous one, RS times CBS plus 1, ठीक है, divided by RS CB, as CB is the bypass capacitance, which are basically bypassing the degenerated response. And also interesting thing, if we do the plot of this thing, we will be end up something similar to this one. यहाँ से this one is basically ultimately adding what? This whole part. It's adding the same thing of a high pass characteristics. Okay. So we have something. Let me just do this. Undo. Yeah. So we have here omega. Okay. Omega is here. We have something going like this. So ये फिर high pass characteristics हो जाएंगे. माइनस और इसको GMRD कर देते हैं. Let's not mind, हम लोग उसका कर रहे हैं. तो यहाँ आपके पास GMRD आ जाएगा, which is at this point. किस point पे आएगा GMRD? When we are having the S is equal to something which is going to be cancel out this stuff. So it will be equivalent to 1 over, just plug in करके you can just figure it out. This thing, this is 1 plus GMRC divided by RS times CB. अगर ओमेगा या जो S की वैल्यू, ओमेगा की वैल्यू ये होगी, then the gain will be equal to GMRD. But at this point, whenever my omega is equal to RSCB, if you just want to plug in, you can just plug in this thing here. Your value of a gain will be GMRD times or divided by 1 plus GMRD. So it's telling us very much nice info. It's basically RS, not RD. So यहाँ में वो ये वही बात बता रहे हैं कि the point whenever the omega reaches this frequency, ये इस फ्रीक्वेंसी पे पहुंचता है, the amplifier starts behaving as a common source. And at this frequency, which is a lower frequency, at that point, the amplifier is ultimately behaving as common source with degeneration. So that's a small benefit of adding the CB in parallel with source resistance, RS. So इसके साथ parallel में करने से क्या होगा मेरे पास कि this will start impacting at a higher frequency and इसका जो impact होगा that will be grounded, short हो जाएगा. हम लोगों ने बात की थी, this is a low frequency capacitance at a higher frequency पे या mid band calculation में I can consider this a CB and my gain will be GMRD. Whereas at a lower frequency, this CB will play its role, and that time any frequency lower than 1 over RSCB, my gain will be equivalent to common source with degeneration gain. So that's why again this CB is configuration is a low frequency capacitance. तो सिर्फ C in low frequency capacitance नहीं होता, also we have another capacitance जो कि यहाँ इसको commonly कहते हैं bypass capacitance. Bypass capacitance, that's also a low frequency capacitance. तो हम लोगों ने analysis point में कहा था, for the low frequency analysis we will consider the capacitance, we will identify them, but in the mid band calculation and in the high frequency response we will do them short, ignore them, meaning we will do all of them short. Short meaning zero कर देंगे, तो zero कर देंगे, RS in parallel zero is going to be zero. Okay, so till now we have seen the low frequency response of a common source. That's a common technique we do, but let's talk about a high frequency response. So for high frequency response for a common source, low frequency common source or common adding CB, हम लोग का response will be same band at a higher frequency. तो ये हमें एक फायदा हो गया with the addition of bypass capacitance. So let me draw the high frequency response and then we can do some analysis. If things are not clear, we are going to do some examples in a smaller time, so the things will be clear in a few more. Now we want to do its high frequency response. हम लोगों ने वो mega L वाली चीज तो देख ली. Now we want to visualize the mega H thing. So इसके लिए first of all what we need to do at this moment, I am not bringing those load capacitance. Let's say they are not provided, but I want to bring all the transistor capacitance. जिसको हमने parasitics कहा था या transistor cap कहा था. So we want to bring all of them. Parasitic capacitance. वो क्या थी? So they will be. Let me draw it separate so you can. And I will draw with the red color on top. So let's इसको बड़ा draw करता हूँ, so all of you can see this thing. Same circuit में, this is a V in, this is RS, this is RL, and here it's a, since it's a high frequency response, तो मैंने अब उसको S को जो source degenerated resistance उसको remove कर दिया. Now let's draw the capacitances. Capacitances कौन सी होंगी? One capacitance will be between source and drain. So this is sorry, gate and drain. So C, G, and D. One capacitance will be gate and source. C, G, S. One capacitance will be between drain and bulk. C, D, B. Now we know here easily, that's why I'm drawing in a different color, that bulk and the source are grounded, so we can explicitly draw कि जो source और bulk की capacitance होगी, I'm drawing at this moment, केवल ignore ना उनका direct करें, वो present होती है, but since source and bulk is shorted, this will also be non-existent. CSP will be non-existence. Non-existent, ठीक है. क्यों non-existence होगी? Because source और bulk short है आपस में. तो हमारे पास जो capacitances हैं, they are CGD, CGS, CDB. And अब किस तरह आगे further we can move on? We can do the small signal model for our simplification, and then we can compare that one with the techniques which we have already learned. Small signal model इसका draw कर लेते हैं. Small signal model में क्या आएगा? We have V in, we have RS, we have RS, RS के साथ क्या चीज है? We have VGS. ये अगर source है तो ये source grounded हो जाएगा. We have a capacitance known as CGS, and then इसके बाद now this point is connected this one, and this is your GM ID. तो ये आपके पास गेट पॉइंट होगा, ठीक है. सो GM1 अगर ये M1 था, GM टाइम्स VGS. अगेन R lambda हम लोगों ने सिंप्लिसिटी के लिए lambda को 0 ले लिया. दिस मींस R नॉट इज infinity. So we will take here RL हो जाएगा, and this point will also be इसको इसके साथ कर दें, all of them are grounded together, ठीक है. So and we have other capacitance. Let me draw the remaining, all the red one to avoid confusion. So this is a drain for us. So there will be one capacitance between CDB. You can and one capacitance CGS हो गई है, and one capacitance between the gate and the drain CGD. ठीक. So now everything is clear. Everything is okay. That CDB will be load capacitance. CGS input side पे आ रही है. But the thing is that just CGD है, that is in the middle between two nodes, gate and drain. इसको किस तरह sort out करेंगे? Miller capacitance के तरीके, which we have already learned के ultimately क्या हो जाएगा? CGD will be divided into two capacitance. जब भी मेरे पास इस तरह के configuration हो with a minus gain, ये CGD है, ये है, तो I can reflect this. Let me reflect it back on this side. इसको किस तरह tweak कर सकता हूँ? I can do this thing. माइनस ए एक कैपेसिटेंस से लोड पे हो जाएगी, जिसको मैं C2 कह देता हूँ आसानी के लिए. एक कैपेसिटेंस इनपुट साइड पे हो जाएगी, C1 कह देता हूँ. एंड व्हाट विल बी द वैल्यूज? इसको CGD रख देते हैं. C1 will be equal to 1 plus gain. It's ultimately negative, but because of the inverting case, it's going to be 1 plus A times CGD. And C2 क्या हो जाएगी? 1 plus 1 over A times CGD. So हमारे पास दो capacitance हो जाएंगी somehow in this fashion. And these two capacitances ultimately will make our life easy. Why? Because the C1 will be added in the CGS and C2 will be added with the CDB. ये दोनों load capacities हो जाएंगे. Our frequency response will be way simpler than we expect. Okay? So we can apply these things and we can easily sort out our analysis. ठीक है? तो ये हम लोग आराम से कर लेंगे. But if we want to write explicitly numbers in terms of क्या होगा, so we can see that जो C1 है, since 1 plus A क्या था हमारे पास? Gain था, inverting gain. तो it's going to be GM times GM1 times RL times CGD. And C2 क्या हो जाएगा? 1 plus 1 over GM1 times RL again CGD. So we can easily write the values as desired, and that will make our life a lot simpler. Okay, so if you have any confusion, make sure to go through that stuff and clarify now anything. So in your book, I would think you have example 11.15, just finding the omega into based on these values, and also example 11.16. Example 11.15 is basically using BJT, but you can use the same values for the MOS. Okay? So आपने BJT नहीं करना, since we are not covering BJT. but you can do the same example using MOS ones, and 11.16 is basically using a MOS. Or we can do a little bit glimpse of 11.16 to have some of the points clarified, and then we can move on towards some further stuff. So in 11.16, what they are basically doing, they are saying, okay, you have your common source. Let me 11.16 example. You have your common source with degeneration. Sorry, you have your common source amplifier, which was here somehow. And you have your all capacitances. See this one, and this one, and you have RS something, you have RL something, you have VDD, and you have here ground. Okay, and this is your V out. ये हम लोगों ने कह दिया this is CGD, CGC. This name is confused sometimes. C drain to bulk. So it will also take small time to get accustomed to, but then it's just a piece of cake sort of stuff. So this is a gate to source CGS, and this is the gate to drain. Okay. So now what the example is saying, example 1.6 is saying during the design process, the student did a layout, and by mistake, what happened, he make the width of the transistor change as compared to the original one, meaning this MOS has some width and length. Okay, हमारी उसकी कोई width होगी, कोई length होगी. So they are saying that you need to find out the students by mistake has reduced the width by 2. If initially it was 2 micron, okay, 2 micron by 5 second 0.18 micron. So what he did mistake happen, he make it 1 micron by 0.18 micron. So they are asking for, you need to find the gain of the system and the poles, meaning you need to find the gain and the poles or frequency response of the system if the width of a system, a width of a MOS or an amplifier जो हम लोग use कर रहे हैं वो half हो गई है. The first thing we need to understand कि width अगर half हो जाए तो what is the impact it's going to create in the overall system. One more thing, they're also talking about the bias current, the I, which is flowing through, that's also is half. So सिर्फ width half नहीं हुई, I is also is half. Okay, so width or this is width or current दोनों basically half हो गए हैं, and we need to determine the frequency response. So first thing, if I is, I'm writing in a green color some analogies. If I is half, I reduced, then the transconductance, which is GM basically, also reduces by same amount. Yes, a little bit look into it. Why? Because that is very much important question. If I reduces, then GM also reduces by same amount. So if new I new, let's say, is equal to I by 2, then GM new will also be equal to GM by 2. You can directly see the relation, and you can see if the other things are remaining constant, ultimately the GM or the transconductance will go down. That's one thing we know, that transconductance goes down. And what is the gain of this amplifier? We know the gain of this amplifier is minus GM times RL. And what is the new gain? This is the old gain, let's say. And what is the new gain? The new gain will be equal to, minus GM by 2 times RL. So the gain ultimately will also reduce down. If my current reduced by half, my gain will also reduce by half. That's one thing. Second analogy, and ultimately one notion I also want to make, if you make the width of a transistor half, it's not like the current we are changing. Current also becomes half if you are keeping other things constant. So even if this information, that width of my system is reduced, then this means the current is also reduced, because the current is going to pass through the MOS. If the MOS has less width, less current will flow through it. The first thing is that the gain, if the current reduces, the same amount transconductance will remove, and the same amount the gain will reduce, because the RL is constant, RL is fixed. Moving forward, the other thing is that pole information. So for pole information, we'll decide in the frequency response. So for before that, we need to write what are the input and output pole information in the this configuration which we just wrote. So previously, if we write the pole information, we have two poles. If we just draw this thing, I'm drawing it again, the pole information. So it will make your life more easy. So we have one source capacitance drain to work, and one capacitance was C2. If you just recall from the previous one, we just see. And similarly, on input side, we have one capacitance CGS, and another capacitance was what? C1. So you can tally the formulas for CL and C2. That CL was 1 plus GM RL times CD C drain to grade to drain, sorry, and 1 plus 1 over GM RL gate to drain. Okay, so ये C1 and C2 हो जाएंगे. So omega Pin will be in counting these two input side पे जो capacitance है, and what is the resistance here? The resistance value was RS. So we can find out easily, or gain, or a new one will be, since the capacitance reduced, so this C1, CGS, everything will be reduced by the same amount. So अगर आपके पास capacitance half हो गई है, this means जो नई pole होगा, that location will be, resistance will remain as it is. So C in जो आपके पास था, यहाँ से CGS था, CGS will be half now, time or plus 1 plus GM RL, gain भी half हो गया, तो GM by 2 RL times C, ये क्या था आपके पास, C1 का CJD था, CJD. So this is the new pole location. इससे क्या पता चल रहा है, अगर मैं इसकी बात करूं, दिस वैल्यू जो डिनोमिनेटर में थी वो रिड्यूस हो गई है, डिनोमिनेटर वैल्यू रिड्यूस हो गई है. सो अगर डिनोमिनेटर में रिड्यूस होगी, मीनिंग न्यूमिनेटर में वो इंक्रीज हो गई है. ठीक है, तो ओवरऑल फ्रीक्वेंसी रिस्पांस ज्यादा हो गया है, बड़ी बैंडविड्थ हो गया. सेम थिंग इफ आई वांट टू डू फॉर द आउटपुट पोल, जो कि डोमिनेटिंग पोल होगा अल्टीमेटली, उसको अगर कैलकुलेट करें, दैट विल बी RL. अगेन समथिंग सिमिलर, सी आउट पे क्या था, CDB by 2, वो भी हाफ हो गया, एंड 1 plus 1 over GM RL 2 पर डायरेक्टली ले जाते हैं, टाइम्स CJD. ये भी डिनोमिनेटर विल गो डाउन, अगर क्योंकि वो रिड्यूस हो गई है पहले की वैल्यू, अगर वो रिड्यूस होगी द फ्रीक्वेंसी विल गो अप. अगर फ्रीक्वेंसी ज्यादा होगी तो हम क्या कहेंगे, bandwidth is increased. So that's a very much important point which I'm going to mention now. Your bandwidth will increase, and that brings us to another terminology which we normally use in amplifiers, the gain bandwidth product, GBW. In a common amplifier, the gain bandwidth product remains constant. If you increase gain, you will reduce bandwidth. If you increase bandwidth, you will reduce gain. How? Let's see a simple analogy in this one. For example, the gain of amplifier is here. This is the gain, right? And this is the bandwidth. If you just, this is your gain and this is your bandwidth. Let's, for simplicity, this is a 3 dB bandwidth, or is a unity frequency. If I just tweak the same thing down, everything else remain the same. What will happen? Here, you can see the bandwidth increased, gain reduced. Similarly, if I further reduce it, the bandwidth increase, gain reduced. So this GWW product all the time remain constant for a specific amplifier. जो भी आप amplifier use कर रहे हैं, अगर आप gain increase करेंगे, the bandwidth will go down. If you reduce the gain, the bandwidth will go up. It's not possible to increase both gain and bandwidth फॉर सेम सेटिंग्स आप नहीं कर सकते। इसीलिए इस एग्जांपल में व्हाट वी डिड, वी इंक्रीज बेसिकली the bandwidth by 2 times and ultimately our gain reduced by approximate 2 times. किस तरह किया है? What we did, we reduced the width to half. Let me just overall conclude this example. हम लोगों ने width को half किया है। width half करने से क्या हुआ? Current become half. Current half करने से क्या हुआ? GM become half. GM half करने से क्या हुआ? GM RL और gain becomes half. ठीक है, गेन हाफ करने से क्या हुआ? अल्टीमेटली और सिस्टम गेन रिड्यूसेस। नाउ समथिंग हैज टू रिस्पॉन्ड। जिस तरह मैंने कहा था गेन बैंडविड्थ रिमेन्स कांस्टेंट, तो वी नीड टू सी द बैंडविड्थ इंपैक्ट। बैंडविड्थ किस तरह देखेंगे? विद द पोल्स, तो बैंडविड्थ बिकम्स डबल। किस तरह देखा? बाय सीइंग द कैपेसिटेंस इंपैक्ट। हम लोगों ने कैपेसिटेंस जाके देखी, द कैपेसिटेंस वर रिड्यूस्ड। अब इंपॉर्टेंट क्वेश्चन आता है कि व्हाई द कैपेसिटेंस बिकम हाफ? capped half. ये एक क्वेश्चन है which you need to ponder, which you need to look over it. The reason is that जब हम बात कर रहे हैं मॉस की, मॉस में क्या चीज है? जिस तरह लास्ट टाइम मैंने कहा था, the capacitance CGS, CGD, CDB, CSB, all are them depending upon the width and the length of this MOS. जितनी ज्यादा width होगी उतनी ज्यादा capacitance होगी. If I increase my width, the capacitance will go up. Same amount. If I reduce my width, the capacitance will reduce. So same thing. मैंने capacity half की, सारी capacitance half हो गई. All the capacitance half, all become half, and that's very much important. And that's what we saw in this example 11.6. So we fought out the things. Right, so there are, again, as I mentioned, there are some good examples. I guess you can do those. They're self-explanatory, but if you again need any help, you can please approach to us. But the examples, for example, 11.17, that's basically comparing the approximation which we use in the Bode plot, or which we use the Miller, and also the direct analysis, the overall, if you do the small signal model and place on the capacitance, do that calculation, and how much approximation basically affect our final results for the frequency response, for high frequency response. No, low mid doesn't matter. So I would highly recommend at least go through, skim through that, read the content, because might be doing that. Math might not be helpful, but those responses are good. But 11.18 is a numerical example. Just plug in some values to have a feeling that how the frequency changes by bandwidth and kis tarah cheezein change hoti hain. So make sure to go through that content also. And one important aspect which we also need to see is ultimately the input impedance. Then we can move towards the common gate. So एक चीज है input impedance. Let me just see. In old times, whenever we do our MOS amplifier, we used to say some things about this MOS amplifier is this one. Your input impedance, which is being seen at this node, is ultimately infinity. ठीक है, हम यही कहते थे कि we are seeing from the gate, so the input impedance is infinity. But whenever we are going to bring the frequency, then this is not infinite anymore. Why? Because now we have this configuration. We have a capacitance and we have capacitance here. So हमारे पास यहाँ एक gate to drain है, यहाँ हमारे पास gate to source capacitance है, and this was resulting into something like this. CGS plus 1 plus GM, अगर वो RL लगा हुआ है यहाँ, GM RL times CGD. So now we have this one, so we cannot say that the capacitor is going to be exact. The Zn is infinite at more because there is some values which is associated to it. So we need to write that value, and that value will be equivalent to reactance basically. So that will be equal to 1 over CGS plus 1 plus GM RL times CGD. And you can see, and it's going to be multiplied with S. You can see it's a frequency dependent. S is kya hai? J omega. As omega is equal to 0, your impedance is infinite. As frequency is increasing, your impedance is reducing. So this is your Zn. अगर मैं Zn plot करूं with respect to omega, we can have this relation. That's also one of the important notion which we can observe, that the frequency which was infinite, we are using taking infinite, it's not infinite anymore, it's a frequency response. The zero frequency DC जो हम लोग पहले analysis कर रहे थे, yes, it's infinite, but as the frequency increases, its value starts reducing, and that's also in the design practice we need to be careful. Now after that, we have to do the same response for ultimately the common gate. So frequency response of common gate. कॉमन गेट, इसमें भी हम लोग उसको दो पोर्शन में डिवाइड कर देंगे. फर्स्ट पोर्शन विल बी लो फ्रीक्वेंसी and second will be high frequency. So let me draw the circuit and then we can draw the low frequency. It will be similar what we have seen previously, nothing new, but just to make sure we cover this point. So RL, VDD, we have here a common gate amplifier connected to ground or bulk or body, whichever you want to say. And then we have something. Now, इसमें important चीज आ जाएगी. We have a here low frequency में we have here a capacitance which is C in, and then we have source resistance, and then here we in. So ये थोड़ा सा variant है. That now we have a capacitance here जो पहले नहीं थी, and that is a कपलिंग कैपेसिटेंस को हम लोग लास्ट लेक्चर में डिटेल में डिस्कस भी कर चुके हैं. कपलिंग कैपेसिटेंस क्या करती है? बायसिंग में सपोर्ट करती है, डीसी कैंसिल आउट करती है. इफ यू वांट टू डू द रिस्पांस फॉर अ लो फ्रीक्वेंसी में, लो फ्रीक्वेंसी का सेपरेट करेंगे, हाई फ्रीक्वेंसी का सेपरेट रिस्पांस करेंगे. सो द वी आउट बाय वी इन फॉर द लो फ्रीक्वेंसी रिस्पांस, अभी और कोई कैपेसिटेंस अज्यूम नहीं करेंगे. इट विल बी समथिंग हाई पास फिल्टर कैरेक्टरिस्टिक्स है. So it's going to be like this, and if we want to draw this one, it will be GM divided by 1 plus जो हम लोगों ने last time भी देखा था, GM divided by 1 plus GM RS, and यहाँ नीचे आपके पास C in आ जाएगा. Let me just rub it correct. So this one ये अब C in के साथ आ जाएगा, and यहाँ gain कितना हो जाएगा? Same as the common gate का, we all know RD divided by RS plus 1 over GM. So we have this gain, which is basically the DC gain ultimately, and ये cut off कहाँ आएगा? Omega L will be equal to GM divided by 1 plus GM RS C. If we want to determine, we can easily determine by this point. यहाँ पोल आ रहा है, यहाँ कैपेसिटेंस कितनी है? C in times किस चीज से